Namaskar, I am Naresh Pant, a professor in Department of Geology, University of Delhi. Today, we are going to talk about X-ray diffraction. The point is that why do we require to investigate a material by X-ray diffraction? The purpose of using X-ray diffraction for geological material is to examine their physical property in terms of its crystallinity. Most of the minerals are crystalline material. Let us first understand what is a crystalline material or what are the special attributes of a crystalline material. A crystalline material can be considered as a regular ordered internal atomic arrangement which can be produced by within quote infinite repetition of a unit. That unit is known as unit cell. We say infinite repetition because the unit cell is very small in terms of angstroms. A unit cell is a three-dimensional entity and it is defined by 6 parameters. These 6 parameters are the 3 axes of the unit cell and the 3 interaxial angles. So, if we can define and work out these 6 parameters, we can define the crystalline structure of a material. Now, these 6 parameters can be considered in terms of several crystal systems, and there are many notations or more than one notation for describing these crystal systems. We generally consider either a 6 or 7 crystal systems. These include the cubic or isometric system, in which the 3 axes which we can name as A, B and C are equal, and the 3 angles which we can name as alpha, beta, gamma. Alpha between B and C, that is alpha between B and C, beta between A angle C and gamma between A and B. So, alpha is angle between B and C crystallographic axis, beta is between A and C crystallographic axis, and gamma is between A and B crystallographic axis. Now, in cubic system or isometric system, the A is equal to B is equal to C, and alpha, beta and gamma are 90 degrees. So, this is one type of unit cell. The second type of crystal system is one where A is equal to B and is not equal to C, and all the angles alpha, beta and gamma are 90 degree, and this is the tetragonal system. We can have, as I said, 6 or 7 ways to describe the crystal systems, and these the extreme end of this is the triclinic system, where A is not equal to B, is not equal to C, and alpha, beta and gamma are non-90 degree. All angles are non-90 degree or non-orthogonal relationship. So, when we use X-ray diffraction, we try to characterize this physical aspect of a crystal and with the aim of trying to know the unit cell. Now, this regular internal atomic arrangement can be defined in terms of lattice points, and a lattice point is representative of similar environment for one particular lattice point throughout the space of a crystal. There can be several types of unit cells. One unit cell, which is known as a primitive unit cell, is like this, which has a lattice point in its center. Now, this lattice point is not shared by any other. So, the number of lattice points in this primitive or P unit cell is equal to 1. In the non-primitive unit cells, the lattice point can either be on the faces, they can be on the corners, or they can be on the edges. The one which are on the corners are shared by 8. So, if we have a corner lattice point, then that will be shared by 8 and its value will be n by 8. Similarly, if we have one on the face, that will be shared by 2. So, face lattice point will be n by 2 and the edge lattice point will be n by 4. So, this way in non-primitive lattice cells, non-primitive unit cells, we can have different total number of points per unit cell. So, with this background of the definition of the crystal, the unit cell which can be primitive or non-primitive, and the crystal systems, we try to investigate or understand the property which we are determining through X-ray diffraction. So, prior to understanding X-ray diffraction, where we are using an X-ray to image this crystalline structure, we will have to understand what is the relationship of the image which is produced by an X-ray to the real or real lattice. The analogy of X-ray diffraction can be understood in terms of image formation described by Abbe theory, which considers that any object scatters the incident light by diffraction. Now, in this figure, we have a diffraction grating or an obstruction to light which allows the diffraction of light. The spacing between the two objects which cause scattering is small a, and the light is coming from this side and is getting diffracted. The angle of diffraction is phi here. The diffraction is leading to formation of image at some distance. This is what we obtain in X-ray diffraction. The distance between where the light is getting diffracted and where the image is forming is mentioned as capital L here. The distinction or difference between the images of the two openings is marked as D in this. Now, we see some very interesting difference, that if an image is to form, there has to be a constructive interference between the two diffracted beams shown here. The path difference between the two will be A sin phi, that is A sin phi, and this is related to the wavelength in terms of h lambda. The other interesting thing we see by this diffraction is that when an image is produced by this one dimensional diffraction grating, then the object has a relationship which is normal This grating is like this, which is normal and inverse to the object. So, we have an image which is reciprocal as well as normal to the original object. If A is smaller than lambda, that is the wavelength of the investigating beam, sin phi will become greater than 1, which is not possible, and thus for diffraction to occur, this condition is not possible. If A is significantly larger than lambda, then diffracted beam will be too close to the direct beam to be seen, and therefore, the two should be nearly similar. The spacing in the diffraction pattern is reciprocally related, as I stated, and the diffraction pattern is normal to the line of grating or periodically spaced object. This leads us to the concept of reciprocal lattice.
Yes, sir. Yes, sir.
For generation of constructive diffraction in 1 or 2 dimensions, the diffracted beams are produced simultaneously without any specific orientation of the incident beam in relation to the object grating. But in 3 dimensional specific geometrical conditions are required to produce diffraction, as it requires simultaneous solution of the 3 diffraction equations. Now, in this diagram, we will have a look at 2 dimensional refraction patterns relating the object and the diffraction pattern, following the Abbe theory which we learnt earlier. In the first diagram, we see the real object, and in the second diagram we see the diffraction pattern, that is A figure represents grating and B represents the diffraction pattern. Following the normal and reciprocal relationship, the distance here, the distance between the succeeding plane which cuts A and B plane at unit distance is marked as D11, D with a subscript 11. Now, this plane is diffracted, and there is another plane which is where the intersection of A axis is at unit distance and that of B axis at half the unit distance, producing a plane D12. Now, each spot in the diffraction pattern refers to particle periodicity in the object. The object periodicities are D11 and D12. Length of the vector from the origin in any spot in the diffraction pattern is reciprocal to the object spacing to which it refers. For example, this is the distance which is 1 inverse of the B axis. The B axis is this, and we see that in the diffraction pattern it is the inverse of the B axis. Direction of the vector from the origin to a spot is normal to the spacing to which it refers. And the second point which we had observed earlier, that is the normal relationship, can be seen here. Now, the one difference which is very apparent in the grating and the diffracted pattern is that there is no origin actually marked on the object, whereas when we are looking at the diffracted pattern, there is, we are considering the origin, and the origin is where the beam is not diffracted. With reference to that, all other planes are diffracted. So, this is a difference between the reciprocal lattice and the original lattice, and this is the case of a 2-dimensional lattice. So, thus a reciprocity with the object on account of which the diffracted pattern is called reciprocal lattice, and the notation for the vector in case of a reciprocal lattice, for A axis is A star, for B axis is B star, and in case of 3-dimensional lattices the notation for the C axis is C star. Since crystals by definition behave as a regularly spaced diffraction grating, their structure can be examined by a probe of a suitable wavelength, and for that the X-ray wavelengths are similar to the differences or distances in the crystal structure. The X-rays have wavelengths varying between 0.1 to 100 nanometer, and that is in order or similar to the spacings which we see in mineral crystals. For parallel planes of atoms with the spacing defined by d HKL, where HKL refers to a particular crystallographic plane, the diffraction occurs only when certain conditions are satisfied, and these conditions are that for constructive interference, and these are defined by Bragg's law. Let us look in this diagram when this condition will occur. In this case, we see ray 1 and ray 2 interacting with a crystalline material with a regular spacing. The difference between atomic plane distance is mentioned as d here. Now, ray 1 is diffracted by a particular angle and it moves here, and ray 2 is similarly diffracted. Now, for a constructive interference, the relation geometrically needs to be satisfied, where n lambda, where n is an integer, is equal to the distance, that is d. So, therefore, A becomes equal to d sin theta, or 2a becomes equal to 2d sin theta, and therefore, we arrive at the relationship, that is n lambda is equal to 2d sin theta, which is known as Bragg's law. Now, if we use in n lambda is equal to 2d sin theta a wavelength of a monochromatic or known X-ray or known wavelength, then we can measure d or the d spacing. Now, this is a typical construction or ray diagram of a construction of a goniometer, wherein the X-ray, monochromatic X-ray of a known wavelength is generated in an X-ray tube, and it is allowed to interact with powdered material which is crystalline. So, this angle is the angle between X-ray source and the sample, and this is the diffracted angle. However, the diffracted angle actually is, as you can see, is twice that of the angle which is there on the incident X-ray. So, this is the instrument is sometimes also known as 2 theta instrument, where the detector is placed and the angle which the sample is making with the X-ray tube, that angle is 2 theta. In theta instrument, the sample is fixed and the tube rotates at a rate which is some degree per minute, and the detector rotates at a rate of theta degree per minute. This instrument which is used to rotate both the X-ray tube and the detector is called a goniometer. The goniometer keeps track of the angle theta, while the detector records the rate of X-ray coming and the other side of the sample in units of counts per second. The X-ray intensity then can be plotted against the angle theta or 2 theta, whatever the case be, to produce a graph, and this allows us to note down specific de-spacing or constructive interference situations satisfying Bragg's law. We can see this in the case in this graph of powdered clay mineral. You can see that this prominent peak at a particular 2 theta value, which signifies a de-spacing of around 3.56 angstrom, is characteristic peak of quartz. As you know, quartz is a pure phase, so its peak is a constant marker. In reference to that, we have other peaks in this, which refers to illite, chlorite, and the second order peaks of illite and chlorite, and the other peak of quartz present in this sample. So, based on the specific de-spacings, one can mark and identify minerals which are otherwise not identifiable by any other method. We will try to understand this generation of such a pattern, how this is generated when a detector rotates with respect to the sample. We will try to understand how this pattern is produced by understanding about a concept known as Ewald sphere. In this we will look at the real lattice and the reciprocal lattice. Now, in this diagram we have a sphere constructed which has the diameter which is 2 by lambda. Remember, lambda represents the monochromatic X-ray which we are using to investigate the crystalline material. Now, if we have an X-ray of 2 by lambda diameter circle, then the Bragg's equation is satisfied in this diagram by 1 by d this plane 320 which intersects on this circle. In 3 dimensional, this circle will represent a sphere. So, wherever this 2 by lambda diameter circle intersects the lattice point, that will mean that the Bragg equation is satisfied. Therefore, the points intersecting on this circle will mean constructive interference, and if we have a recorder or detector moving along this and this point is intersected, a constructive interference or an X-ray peak will be recorded. So, in a particular position in this plane 320 plane is intersecting with reference to 000 or origin in this reciprocal lattice. Now, we tilt the detector by an angle of 10 degrees, and as we tilt some other points intersect. For example, point bar 130 now intersects the circle, and that means that now the Bragg equation is being satisfied for this plane, and we will be recording the X-ray peak for this plane. So, continuous movement of the detector leading to movement of this circle in such a manner that it intersects different planes will lead to identification or satisfaction of Bragg's equation for different planes, and therefore, the continuous movement will lead to recording of the X-rays for different particular planes. So, the sphere which defines in 3 dimension, which is defined by the diameter 2 by lambda, represents a concept on the surface of which the Bragg's equation is satisfied, and this is known as Ewald sphere. And this is the idea which allows us to signify and note various crystallographic planes. Well, we can see this in another diagram where we are looking at a figure or a concept known as Debecon. The X-rays are coming like this and interacting with the crystalline material. Now, the area in which a particular plane will lead to construction of a circle is this, and when we join it with the place where the interaction is taking place, this works out to be a cone. Now, this cone will satisfy the Bragg's equation, and this is known as Debecon. And if, as it used to be there in earlier time, if we were putting a film around this, we will be recording the Debecon as lines along this. The relationship between the lines on the film is a linear or distance relationship, and that needs to be solved for the angular relationship, and this is given by S by 2 pi r is equal to 4 theta by 360, whereas S is the distance between the two lines here. So, this can also allow us to record the constructive interference of each particular plane in this fashion, and they can be therefore thereafter indexed or worked out that which plane to which it belongs. For doing that, there is a Joint Commission on Powder Diffraction Standards or JCPDS, which has a vast library of powder diffraction patterns of thousands of crystalline substances. Since every compound with the same crystal structure will produce an identical powder diffraction pattern, the pattern serves as a kind of a fingerprint for the substance and as an identification tool. But if there are intergrowths present and minerals with complicated structures on account of impurities in their composition can lead to variation of this. But it does provide us an identification tool for minerals which cannot be identified otherwise. So, we have learned today that minerals mostly behave as crystalline substances, and to investigate this nature, which is defined by a small unit or unit cell in their structures, we can use X-ray diffraction. For X-ray diffraction, we use a monochromatic X-ray, and the interaction constrained by the Bragg's law of constructive interference produces the crystal planes, which we can index, measure and characterize in terms of their crystal structures, which in some cases can be used as fingerprinting for those minerals, and in other cases can be used to deduce other crystallographic parameters of that material. Thank you.